All right, so I'm recording now. Um, it's it's um it's creating the video from the last half, and the fan is on. Is my Can you guys hear my fan? Is it distracting hearing the fan of my computer on? Okay, good. Um,
No.
that's good. Okay, then we'll just continue on. That's why I was kind of delayed. I was trying to wait until the fan turned off, but it doesn't look like it's going to turn off anytime soon. So let's just get going. Um, Definitely have plenty more stuff from chapter 4 to talk about. Um, So we've talked mostly about sensory memory, that is iconic and echoic memory. Uh, yeah, that we basically talked about sensory memory, auditory, echoic, and iconic memory so far. Now, and we also talked a little bit about short-term memory. We used the Miller task, which is thought to be more of a measure of short-term memory. And now we're going to talk some more about, we're going to move away now from sensory memory and talk more about short-term and long-term memory for the remainder of this chapter. Um, and so first off is a term that I talked about a little bit with respect to the Miller task, which is chunking, also known as recoding. Conceptually, the important thing about chunking, and it says it here, is it blurs the line between short-term memory and long-term memory. Whoops. And I'll explain what I mean by blurs the lines between short-term memory and long-term memory in a second. The idea of chunking is that you're performing a task which on the surface, why are you doing that? Oh, the video's done. Sweet. On the surface, you're performing a task which looks like you're using your short-term memory, but it actually turns out that behind the scenes, your mind or your brain is actually using your long-term memory to make the task a little bit easier than it would otherwise be. And that's the idea of chunking, using your long-term memory to kind of boost your performance on what appears to be a short-term memory task. So let's, I think we got an example here. Can't see my mouse. There we go. Okay. So here's a more formal definition of chunking. Um, and here's the example. I'll just go straight to the example. So you guys can't see my desktop, right? You can't. Oh, okay. Surely now you can see it. Okay. Please, in the future, if it looks like I'm talking about something on my desktop and you can't see it, please call me out because I don't want you to sit there not looking at what you're supposed to. Occasionally, I make mistakes and forgot to press the share button, which is what happened here. So please call me out for that in the future. Okay. But we didn't miss much. All I showed you was what did I show you? This chunking versus recoding, blurs the lines between short-term memory and long-term memory, and this thing right here. All of this is in the slides, which I posted on Blackboard. So moving on then to our example. So here in these examples right here, imagine that you're performing kind of like a Miller task, but we're using letters this time. And remember the Miller task, I read you off a sequence of letters. In fact, we can do that. Maybe don't look at the letters and let's see how easy these tasks are for you. I'm going to read you off the sequence of letters, and I want you to repeat back to me all of the letters. Okay, you guys ready? So here's the first sequence. So don't look at them, just try and listen and try and repeat back as many as you can. A, B, C, T, N, T, E, S, P, N. Verse, okay, so that was that one. Did anyone think they got all 10 of the letters?
A B C T N T E S P N.
You got it. Excellent. I was kind of nervous. I've never actually done that live before like that. I was kind of nervous that no one would get it. Thank you, Stephanie, for getting it there. So that was good. So you got all 10 letters, which is kind of impressive if you think about it, because if you guys heard about the Miller task, maybe in your intro psychology class, the average, does anyone know it's 7 plus or minus 2 is typically thought to be the average capacity in the Miller task, and you just got one for 10. So 10 letters is pretty hard to get in a short-term memory task. Usually the capacity of short-term memory is assumed to be only 7. And so what you just did was 10 letters long. And so it appears that you are using more than just your short-term memory to do that. You are probably using your long-term memory, and we'll get more back into that in a second. Now let's try the other sequence. CBANTTNPSE. So that one's hard.
It's already on the screen now.
What?
It's already on the screen.
Oh, I know. I told you not to look at it when I was doing it. But yeah, I mean, you get the point. I mean, I know it's on the screen, but the idea is which one of those two is easier, which one's harder?
The ABC, TNT, ESPN.
That's
It's
easier.
easier.
Yeah. So can you explain to me why?
I'd say it's easier because those are like things you're familiar with because they're networks, ABC, TNT, and ESPN. You know?
Exactly. They're networks, they're television networks. And if you watch TV, they're common American television networks composed of, they're acronyms, letters that compose the name of the networks. So in that top example, it's like you're not really having to remember 10 things anymore. Instead, you're memorizing like 3 things, 3 television networks, ABC, TNT, ESPN. That's the whole basis of chunking. You're taking a whole bunch of stuff that you would otherwise have to remember with your short-term memory, but you're using your long-term memory to kind of offload, to help. You're using your long-term memory to boost your performance on what appears to be a short-term memory task. This is basically the Miller task, except here you're able to use your long-term memory. Down here, I want you to notice it's the exact same letters. I've just scrambled the order. If you look, the letters are the exact same. The only difference is down here, the letters don't form television stations. And so people do worse on this one than this one up top. Up top, they do better because only the top one are you able to chunk. Only the top one are you able to use your long-term memory to boost your performance on this task. So here is, let's have to close you out for a second. So here is a study published in Science, so a really prestigious journal, one of the best in the United States. The journal Science published this, gosh, it was probably 40 years ago now, though. And this was a study, one of the first studies that illustrated the incredible power of chunking. So this study used a single participant, and this single participant was just a normal person. I don't know if it's a man or woman, just a normal person that came into the laboratory every day for, it says 85 days, but I believe that's a typo. It would be, whatever 5 times 35 is. 5 times 30 would be 185 days. So I forgot the one there. They came into the laboratory for basically 185 days, or almost basically a half of a year. They come into the laboratory every day and they perform the same task every day. And that task is the digit span, the Miller digit span. I give you a sequence of numbers and your job is to remember the entire sequence. And that's time. This is day 1 over here, day 2, day 3, day 4, day 5, all the way through day, these are in 5-day blocks. So this is day like 185 way over here. And on the y-axis, they're measuring digit span. Digit span is basically how many digits are you able to remember? So on day 1, the participant's pretty normal. He is within the typical short-term memory threshold. I said earlier, most people kind of assume that the typical span of short-term memory is 7 plus or minus 2. And this guy looks like he's a little bit higher than that. He's about 9, which is definitely within the range, though, definitely within the margin of error. On the very first day, his average score, he was able to remember digit sequences that were 9 digits long. Pretty typical performance. But as you look at his performance over time, by the end of the experiment, he was able to hear a sequence that was 80 digits long, and he was able to remember those easily. His average sequence that he could remember on the very last day was 80 digits long, which means he had no problem hearing sequences that were 75, 80 digits long and remembering the whole darn thing and repeating it back to the experimenter. So this illustrates chunking. First off, the gradually increased digit span over time. I think someone's microphone's on, by the way. If you could turn it off or mute it, I'd appreciate it, at least for now. If you have questions, feel free to unmute it. But for now, please mute it, whoever that is. But the participant, when the researcher asked him, so you have a, at the end of this experiment, the amount of numbers you could remember was freakishly good. How are you doing that? And the participant reported basically what it looked to be a chunking strategy. I think I describe it here in the next slide. Nope, no, I don't. I might say it in the notes. So I'll just tell you what the chunking strategy was in case I didn't write it in the notes. The participant was a runner, and he read running magazines. And in the running magazines, one of the things I've never read one, but one of the things apparently they talk about is famous running times, like the fastest marathon time, the fastest half marathon time, the fastest 40-yard dash, the fastest, it's like 1/4 of a mile time. So what is that, 400 meters? 400 meters is one lap around the track, fastest 400 meters. And so this guy basically had read all these running magazines because it was his hobby. And so he had all these number sequences stored in his long-term memory. And what he reported was that as the task went on and on and on over the sequence of days, when he would hear a sequence of numbers, instead of remembering the sequences with just a short-term memory, he would start using those sequences in long-term memory. And as he would hear it, he'd be like, oh, the number sequence I'm hearing right now happens to be the fastest mile run ever. Or now I'm hearing a number sequence is the fastest 40-yard dash. And so as he was hearing number sequences in his headphones, he was able to map them on to number sequences, famous running times that he had stored in his long-term memory. And he was able to use the strategy, and he mastered it gradually over the span of the experiment. So that once again, by the end of the experiment, he's able to remember a sequence of numbers 80 digits long. So instead of remembering 80 separate things, he was breaking it down into chunks. The chunks that he was breaking it down into were, someone tell me, what were I just said it, but I want to make sure you understand. How was he chunking this? What was the knowledge he was using to chunk?
He was relating it to things that he knows, like times of marathons or dashes.
Yep. The things that he knew exactly were the running times for the marathons and the different dashes. So he was chunking it using his knowledge of race times, which he has stored in memory. So that's chunking, and that's probably the most famous experimental example that I know of chunking. That paper's been cited like 2,000 times. Okay, a little bit more. Now we're moving into primacy and recency effects, this is still kind of getting at this difference. It's still kind of distinguishing between short-term memory and long-term memory. So the way the primacy and recency effects work is that me as an experimenter, I would give you a sequence of numbers which is long. It'd be like 30 or 40 or 50 digits long, maybe 20 to 50 digits long. And I read off the whole sequence of numbers, or maybe it's a whole sequence of letters. And your job as the participant is just to remember as many of the numbers as you possibly can. Remember as many of the numbers as you possibly can. So by the way, how is this task different than the Cowan task? In the Cowan task and this one, you both hear long sequences of numbers. How is this one different than the Cowan task as far as the instructions that you, the participant, are asked to perform? I'll say it again. In this task, you're given a long sequence of numbers, and you're asked to remember as many of the numbers in the sequence as possible. How is that different than what people are asked to do in the Cowan task?
In the Cowan, you were supposed to just remember as many as you can of the last portion.
Exactly. In the Cowan task, you're only asked to remember numbers at the end of the sequence. So this one's a little bit different. In this one, you're asked to remember as many of the numbers as you possibly can. So that might include numbers at the beginning, some in the middle, some in the end. And really the question which is asked in this research is, if I present a long sequence of numbers to people, which parts of the sequence are they most likely to be able to remember? Are they most likely to be able to remember numbers that were said at the very beginning of the sequence, numbers in the middle of the sequence, or numbers at the end of the sequence? And what has been kind of repeatedly shown is these two effects, the primacy effect and the recency effect. The idea of the primacy effect is that we're actually pretty good when you first hear when you first hear a sequence, you're actually really good at encoding those numbers at the beginning of the sequence into long-term memory. And so numbers at the beginning of the sequence tend to be remembered better than numbers said during the middle of the sequence. You tend to forget numbers in the middle of the sequence. That's primacy effects, the fact that you're better for numbers at the beginning of the sequence compared to numbers in the middle. And I'll explain why, but just maybe you should write down now or encode into your memory. Primacy effects are believed to rely strongly on your ability to encode information into long-term memory. Recency effects, on the other hand, is the idea that you tend to better remember stuff at the end of a sequence compared to things at the middle. So if you kind of think about what I've just shown you, primacy effects are the idea that we are really good at remembering stuff at the beginning of a sequence. Recency effects are the idea that we're really good at remembering stuff that occurred at the end of the sequence, which means that we're worst at remembering stuff that occurs in the middle of the sequence. And I'll show you some data that supports that. Before I go on, I guess I need to mention recency effects recency effects are thought to rely primarily on sensory or maybe short-term memory, whereas primacy effects are thought to rely primarily on long-term memory. And so here is some data. Serial position is just the number of digits, or the number of, let's say, yeah, I believe these are digits. The number of digits that are spoken in a sequence. So the orange line is if I give you a sequence that has 20 digits in it. The red line is if I give you a sequence with 30 numbers in it. The blue line is if I give you a sequence with 40 digits in it. So really long sequence, medium-sized sequence, shorter sequence. And what we could see here, well, let me see if you can interpret this first. First off, you can see the accuracy for whatever color the line is. You can see the accuracy tends to be really low in the middle of the sequence. The middle serial positions is lowest. But I also have another question. Based on what you see here, which effect appears to be stronger? Our recency effects appear to be stronger, or our primacy effects appear to be stronger?
Recency?
That is correct. Recency effects. Remember, a recency effect is the idea that the stuff that you hear at the very end of a sequence. So if you're hearing a 20-digit sequence, these are the numbers right here that are occurring at the end of the sequence. You're really good. You can remember almost 100% of those, the numbers at the end of the sequence. But you notice that for the numbers at the beginning of the sequence, you still get this little burst right here. You're pretty good at numbers at the beginning of the sequence, but then that quickly goes down. And the numbers in the middle, you do bad at. You're not very good at remembering those. But then you get good at the numbers at the end of the sequence. And you can see that for 20 sequence, 30 or 40, we're really, really good at the stuff at the end. That is recency effect. We're pretty good for the stuff at the beginning. That's a primacy effect. But we're really bad, no matter what, we're really bad for remembering the numbers in the middle of the sequence. So this chart, these data are the classic primacy and recency serial position curves. So now this is probably the hardest part about this. And this is a part that I'm going to ask you about for next week's in-class quiz. It is also something that I'm definitely going to test you about for test 2. I know from my experience teaching this class and from talking to other cognitive psychology teachers, that this is, for whatever reason, one of the parts which students forget. And it's one of the parts that's most important. And having a deep conceptual understanding of primacy and recency effects requires you to understand the stuff that we're about to talk about. So I just want to emphasize this before we talk about it, because this is important and it's something that I 100% am going to ask about on test 2. So I made the claim earlier on a couple slides ago that primacy effects rely primarily on long-term memory and recency effects rely primarily on short-term memory. What is the evidence that actually supports this? What evidence supports the idea that primacy effects use long-term memory and recency effects rely primarily on short-term memory? And the effect, or the primary evidence, is listed here on this slide. So for the primacy effect, and I'll explain what I mean, I'll show you some data here in a second. For the primacy effect, the paradigm involves you do the same task. That is, you give long sequence of numbers and have participants remember as many of the numbers as possible. But for this particular experiment, which shows that long-term memory, or at least it's been suggested, its data shows that long-term memory is important for the primacy effect. Another independent variable which is introduced is the speed of presentation of the stimuli. So you can either have a really fast presentation of the numbers, 1, 3, 4, 8, 6, 9, or you can have a relatively slower presentation of those stimuli, 1, 3, 4, 6. That's a relatively slower one. And so you would present the digits or the letters, you present the stimuli at either the fast pace or the slow pace for the entire sequence. And what they want to see is, how does the speed with which the digits are spoken, how does that influence the strength of the primacy effect? And then let's see, we have that right here. This is taken from another textbook. So I need to explain a couple things, and I might need to minimize you guys. Yeah. So once again, serial position is shown along the x-axis. We have a primacy effect. We have a recency effect. But the really crucial thing here in these data are understanding the difference between the three colors right here. So I need to, the three colors, the single, which is the red line, that in the single, the rate of saying things was fast. So the single, the red line, I was saying things fast, like 3, 6, 9, 2, 1. In the triple, I'm saying things way more slowly. And this, according to this the figure from this other textbook, in the single condition, you're hearing a digit every 3 seconds. So that's relatively fast. In the triple condition, you're hearing a digit every 9 seconds, which is very slow, like 3. Wait 9 seconds, 6. Wait another 9 seconds. And the question they have is, how does changing the rate of presentation influence the strength of the primacy effect? And so you tell me, looking at these data, if you want to have a strong primacy effect, do you want to hear a list in which the digits are being spoken quickly, or a list in which the digits are being spoken slowly? Someone tell me.
Slowly.
It is slowly. And you know that because if you look at the triple, that's when the digits are being said most slowly. That's when you get the biggest primacy effect. Primacy effects, when you're looking at those, you're always looking, how good are people at remembering the digits in the early positions, right at the beginning of the sequence? And you could see that the orange line, that is when the sequences are being read slowly, there's a great advantage towards the beginning of the sequence. The blue, which is the middle speed, is a little bit worse. And then the worst performance is in the red, where the accuracy is lower. But an important question is, did the rate of presentation in this study have an important influence on recency effects? I see one person shaking their head no. Would you mind explaining someone, like, why do you say that the rate did not have an appreciable influence on recency effects? What are you seeing in the graph? That is true.
All three of the lines are relatively similar.
Yeah, where?
At the end.
At the end, that's the crucial thing.
Yeah.
Looking at these lines right here, you can see that they're all overlapping. There's having really, really slow speeds does not help your recency effect, but it does help your primacy effect. When things are said slowly, that boosts your primacy effect, but it does not, and that's important, it does not have an influence on your recency effect. And so now we need to speculate, and this is what the researchers have done here. Why does having a slower rate. Why does that improve your performance for the stuff at the beginning of the sequence? And the answer that has been provided is that it's kind of there's two things you kind of need to mention. When the rate is slow, that gives you more time to rehearse the numbers. So you hear a number and you wait 9 seconds. That gives you a lot of time to rehearse that information, to say it to yourself over and over again, or maybe even to chunk that information. The assumption is, though, is that the more time that you have to practice that information, the numbers are coming slowly, the more time you have to practice, the more time you have to think about it. What that does is that increases the likelihood that that information is going to be stored in your long-term memory. That is the assumption. The more time that you have to practice, the slower the numbers are said to you. The assumption is that increases the likelihood that that information is eventually going to get to long-term memory. And if it's in long-term memory, that's going to help you remember that stuff. So I'm going to repeat the punchline. The fact that you see a greater primacy effect when the rates are slow indicates that long-term memory is more important for primacy effects. That long-term memory is particularly important for primacy effects. The idea is that when the rate is slow, you're more likely to encode that information into long-term memory. So that's the first one here. Move you guys back down. Rapid presentation of stimuli causes a weakening of the primacy effect. And just the same thing of saying if you have a slow presentation, that boosts the primacy effect. And then I wrote the explanation here, which I'm hoping writing out the explanation makes it more likely that you'll remember for the test. Okay, so that's the evidence that primacy effects rely strongly on long-term memory. So now we need to have the evidence that recency effects rely primarily on short-term memory. And so the evidence that recency effects rely primarily on short-term memory comes from studies in which people have to do what's known as a backward counting task. So what happens is that I give you the sequence of numbers that you have to remember. So I say a long sequence of numbers, 20 digits long. And then before I ask you to say that number sequence back to me, I require you to do a task which is called backward counting. And in the backward counting task, I might say, start at the number 578 and count by threes back, like go like 578, 575, 572, 569, and do that for a certain amount of time. So I'm going to repeat this. I give you the sequence of numbers to remember. And then when that sequence ends, before I ask you to repeat what you just heard, I require you to do this kind of backward counting task. The reason why I have you do that backward counting task is because that backward counting task, and it says right here, it's assumed to occupy your short-term memory. It's assumed to make it, though, that whatever information you were storing in your short-term memory from the numbers that you were just supposed to remember, if I'm requiring you to do backward counting, that's occupying your short-term memory. So the numbers that you just had stored in your short-term memory from the sequence of numbers that you're supposed to remember, that information is going to decay because you're not able to devote your attention towards remembering those numbers from the sequence. Instead, you're having to devote your short-term memory, your attention to this weird backward counting task. And so the question is, how does backward counting, which is assumed to rely on short-term memory, how does this interrupt? How does this influence your performance in the recency effect? And so here I'll show you this. So here is another, let's see if I can leave you there. So once again, this is serial position of the numbers. So you're having to remember 15 numbers in the sequence. You're remembering 15 numbers. So the red, blue, and yellow lines differ in the amount of time that I require you to do backwards counting. So remember, so for the red line, for instance, I read off the sequence of 15 numbers, and this is like the control condition. You're not doing any backwards counting at all. In the red line, when the sequence is done, I just say, okay, repeat the sequence back to me. And then for the blue line, the sequence is done. I read off the 15 numbers. The sequence is done. And then I tell you, I want you to perform backwards counting for 10 seconds. And then I want you to repeat back to me the sequence of numbers that you just heard. And the yellow line, which has that in that condition, you were doing backward. You heard the sequence of numbers. And then before you responded, you counted backwards. You did the backward counting task for 30 seconds. And then after that 30 seconds was done, that's when you gave me the answer. That was when you repeated back to me the numbers that you had heard in the sequence. So someone tell me, in which of these three conditions is the recency effect the strongest? The red, blue, or yellow? In which of those three is the recency effect the strongest?
Red.
The red is correct. Another question which is important. In which of these three situations were people using their short-term memory the most to perform the backward counting task?
The red.
It is not the red. It is actually just the opposite. In the red one, you're not performing the backward counting task at all. You're performing the backward counting task for 0 seconds. So you're able to, in the red line, you're able to devote 100% of your short-term memory to remembering the numbers at the end of the sequence. So the red line is where you're able to devote all of your short-term memory to remembering numbers, and you're not being distracted by the backward counting task at all. Your short-term memory is being occupied or being used the most by the backward counting task when you're having to do it for 30 seconds. You're no longer able to use your short-term memory to remember the numbers in the sequence you just heard. Your short-term memory is being occupied by that annoying backward counting task. And that's why you don't see a recency effect here, because your short-term memory is occupied here. You're not able to use your short-term memory to remember those things at the end of the sequence. When in the 0 condition, when you're not having to do any backward counting, your recency effect is still pretty darn good. Tell me this. Does it appear that there is an appreciable influence of backward counting on the size of the primacy effect? What do you guys think?
Will you repeat the question? You kind of cut out on my end for a sec.
Sure, no problem.
Thank you.
So I'll repeat it wholly. So you can see that there's a large effect. Backward counting is clearly having an influence on the recency effect, such that when you have to do a lot of backward counting, that is when your short-term memory is occupied by backward counting, you basically get no recency effect at all. Is there an appreciable or similar influence on the primacy effect? I see one person shaking their head no, and that is correct.
No.
That is correct. There is very minimal, if any, influence on the primacy effect. And so this is really getting into the core of the things I want you to understand about this evidence that says short-term memory is important for the recency effect. Long-term memory is important for the primacy effect. This is the evidence that suggests that short-term memory is important for the recency effect, because when your short-term memory is being occupied by that backward counting task, the recency effect completely goes away. So I will definitely give practice for these on the in-class quiz next week, and some questions about these two studies, this one and this one, will definitely be presented in. There'll be some questions about these in the test. That is basically 100% guarantee. So are there any questions about them before we move on? Okay, so I want to talk about one last thing, and then I'll let you guys get out of here. Well, then I'll let you start your quizzes, and then you can get out of here. Individuals with so the last part. This is evidence that more evidence that primacy effects rely on long-term memory. So this is an evidence from people with amnesia. And this is a specific type of amnesia where people have problems with long-term memory. So amnesia is often portrayed on television and movies and stuff. Amnesia is basically the inability to remember stuff with your long-term memory. People with amnesia oftentimes can remember stuff with their short-term memory, stuff that just happened. But stuff that happened days ago or weeks ago, months ago, people with amnesia are no longer able to remember that. Amnesia here is an impairment in long-term memory. And what is found in some studies on people with amnesia is that if you do this, the number sequence memory task, people with amnesia, they still show really strong recency effects. That is, people with amnesia, they still have this bias where they're really, really good for number sequences, for the numbers at the end of a sequence. But what you find is, well, actually, I don't want to tell you. I want you to look at it. Let's see, trying to remember the difference between these. Right, so this is the one that I want you to look at, this one right here. This is the one that matters most. Here's people with amnesia. Here's people with controls. People without amnesia controls, they don't have long-term memory impairment. And this was a 10-item sequence, so they had to remember 10 numbers. First off, clearly there is a recency effect. But if we're looking at these last like 8 digits, 8, 9, and 10, would we say that are the amnesics appearing to show a recency effect?
Yes.
Yeah, it looks like they're having a recency effect. People with amnesia and the controls are clearly best for the numbers at the end of the sequence. And there's really not a difference between the amnesics and the controls for the recency effects. Basically, people with amnesia and controls, they both benefit about the same from their short-term memory. But what do we think about the primacy effect? What's going on here? Do amnesics and controls, do they have the same strength of primacy effects?
The amnesics show a weaker primacy effect.
Yeah, it does appear that the amnesics have, it's a complicated data set, but if you look right here at the beginning, the amnesics are, the controls, the dotted line, are clearly performing better for numbers at the beginning of the sequence compared to the amnesics. So the fact that this basically shows that people with the controls, they have a relatively stronger primacy effect. They benefit more from the numbers at the beginning of the sequence, presumably because controls are able to use their long-term memory. Whereas amnesics, they do show a little bit of a primacy effect, it looks like, but you can see there's like a 20% difference right here. The controls are way better for remembering numbers at the beginning of the sequence compared to amnesics, who are 20% worse or so on average. So what this suggests is that the people with amnesia are not able to use your long-term memory to the same extent as the controls are to help them remember the stuff at the beginning. The primacy effect in people with amnesia is weakened because of their inability to use their long-term memory. But what's really, really cool about this, and something I want to reiterate, is that it's not like people with amnesia are just bad at everything. They're actually quite fine at remembering stuff at the end of the sequence. So it's not like their memory is just bad across the board. It's a specific aspect of their memory which is impaired. The long-term memory is impaired, which causes them to have an impairment in the primacy portion of this, the numbers at the beginning. Their short-term memory is intact, which allows their performance, the people with amnesia, to be relatively preserved. It's intact. They're not having a problem with their short-term memory. Okay, so I think that's a pretty good place to end this lecture. So let me turn off the, well, actually, I'll show the questions from Origin of Consciousness for the people that are not attending live right now. Do I have those right here? That's not it. That's not it. I guess I'll have to go in here to get it. Here they are. So I'll leave this up here for a few seconds so that the people who are going to watch later can, well, if you want, you could take pictures of these right now. For people later on, obviously, you can just pause it right here and you can do the questions right here. I'll be posting the turn in for this as soon as class is done. Okay, so with that, oops, let me get you back so I can see you guys real quick. Oh, you're down here. Okay. Okay. So with that, what I'm going to do now is I'm going to close the meeting just so that the video that's being recorded right now, I have to close the meeting in order for it to start uploading. So I'm going to close the meeting for like 30 seconds and I'm going to come right back. For those of you that want to try breakout rooms, I'm happy to try that. I have done it once before. I might be a little bit clunky at it doing it today, but I'm definitely willing to try. Or I can help guide you by talking to you and maybe looking at your screen. I can guide you through the process of hooking up with your classmates via Zoom. So I'm going to end the meeting, but I'm going to come right back. So I'll see you guys I'm going to end it now, and I'll come back in about 30 seconds to a minute.